in the sample based on pure chance. Okay, which of the following two distributions is more likely to occur based on chance only, which is the null hypothesis? This is the left one with expected 50-50, and I get 12 blacks and 88 reds in my sample, or is it more likely that purely by chance I'm going to get 45 and 55? Okay, in this one there are large differences between observed and expected, and in this one there are small differences between observed and expected. What do you think? Well, the chi-square formula is chi-square equals the sum times the frequency observed minus the frequency expected squared divided by the frequency expected. Okay, and here's a little legend here for you on the bottom: the observed frequency in any cell and the expected frequency in any cell. Okay, the numerator in the formula means that the difference between what is observed in the data, F observed, and the hypothesis, which is the frequency expected. All right, why are the differences squared? Well, come on, you remember that from the sum of squares, right? We square them to ensure that all values are positive. We get rid of the negatives, like when we measure distance. All right, why divide by the expected frequency? All right, here's Gravitter and Wallnow says that because the magnitude of the discrepancy between the observed, okay, which is my frequency observed, and the expected frequency expected frequencies depends on the size of the, not the observed frequency, but the expected frequency. Okay, so the example is 40 more guests than expected show up at a party. Do you have enough chips and ginger ale for everybody? Question: how many? So the expected, it's based on the expected. Question: how many people were you expecting in the first place? 10 or 1,000? All right, it's the expected that makes the difference. Let's compute it. Let's compute chi-square step by step. All right, this is a goodness of fit example because we're not looking for a relationship between two variables. Okay, so here's the observed, here's the expected, here's the difference squared, and the difference squared of the expected. Okay, so let's step through them. The observed is back there for 1 is 12 and 80. For example, 1 was 12 and 88, and here's the observed, and here's the observed. Okay, step over to the expected. It's 50 and 50, and the difference is negative 38 and plus 38, and I square the difference. There's, see what I'm doing? It's 1,444, and the difference squared divided by the expected, okay, which is down here, is 28.88. Okay, so the sum is 57.57. That's both of those summed up. Okay, let's compare them. All right, the two chi-squares compared. Here's the observed and the expected, and these were the two different distributions. Here, the sum is 57.77, and here the sum is 1. What does this all mean? Well, remember that expected frequencies are theoretical. All right, they are obtained if there is no association between the variables. In other words, if my null hypothesis is true. Okay, we have a measure for the difference between what is observed in the sample and what we would expect to obtain based on chance or just random variation. Remember probability? That's why we looked at probability. The chi-square statistic becomes larger as the difference between observed and expected increases. Okay, so that number, just going back here, the chi-square, 57.77 or 1, is the chi-square, and this gets bigger as the expected and the observed are more different. Okay, let me pop over here back down to where we were. A high value of chi-square suggests that we can reject the null hypothesis. So that one that was up in the 50s, we're pretty sure we could get rid of the null hypothesis. And how do we know what constitutes a high value of chi-square? We know that 57 is higher than 1, but what does that mean? Well, we draw samples of marbles from the jar again and again, an infinite number of times. All right. Each time we compute the chi-square value, we will soon find that the higher chi-square values are less likely to occur. So we plot the chi-square values against their likelihood, and that yields the chi-square distribution. And the chi-square distribution is the set of chi-square values for all possible random samples when the null hypothesis is true. Is this making sense to you? Two important characteristics of the chi-square distribution are, one, that you can never obtain negative values for chi-square because the formula adds squared values. So if you get a negative value, go back and check your math. And two, when the null hypothesis is true, the observed frequency values will be close to the expected frequency values. In other words, when the null hypothesis is true, the chi-square value will be small. Here's the chi-square distribution. They're always positively skewed, and you have to. There's something called the critical region, which is located over here in the extreme tail of the curve. And this reflects large chi-square numbers. Okay, numbers of categories and degrees of freedom. The chi-square formula requires you to add values for each category. So it makes sense that the more categories you have, the larger the chi-square value is going to be. You need to take this into account when you're assessing whether you need to reject or fail to reject the null hypothesis. What the heck is a degree of freedom? Well, so the cutoff points for chi-square differ depending on how many categories that you have. All right, statisticians use the term degrees of freedom to describe the number of values in the final calculation of a statistic that are free to vary, or numbers of free choices that you could have. Example, distributing candy in class. Another example, classifying individuals into 3 categories. You're free to select the percent of frequency for 2 of the 3 categories, but the last category, you only have 1 left. You don't have any more degree of freedom. Okay, just for the 2 first categories do you have some degree of freedom. The last one, you got 1 left. That's it. Here's an example. Let's classify individuals into 3 categories. Okay, so the introvert and the extrovert. Once we have specified 3 values, all remaining frequencies are determined by row and column totals. So you only have 3 free choices. So the degree of freedom equals 3. Here's the formula for degree of freedom. For a two-way chi-square table, degrees of freedom are based on the number of cells for which you can freely choose expected frequencies. Row and column totals restrict your freedom in selecting expected frequencies. Okay, we can freely choose all but 1 expected frequency in each row and column. Okay, hence the formula degree of freedom equals the number of rows minus 1 times the number of columns minus 1. Here's a portion of the table of critical values for the chi-square distribution. If you look in your textbook in the back on page 737, this is just the first few rows and columns of that table. All right, and this is what you use to determine, based on the degrees of freedom, what the proportion in the critical region is going to be. All right, and we'll talk about that a little more. Here's the steps to compute chi-square manually. Okay, the first thing we do is state the null hypothesis and the alternative hypothesis. The second thing is that we observe the distribution of frequencies in the cells of a table, the observed frequencies, and compute the sum for each row and column. We just add them up. 3. Compute expected frequencies, row total times the column total divided by the total number of observations. It's the formula that I had up on the screen before. Then we apply the formula and compute the chi-square statistic. 5. We determine the degrees of freedom that we have. And 6. For the computed values of chi-square and the number of degrees of freedom, use the chi-square distribution table in the back of the book to determine whether the association between the variables is statistically significant. The standard degree of significance that we're going to use is 0.05. We talked about that last week. That gives us a 95% chance of being correct that the variables in the association between the variables is statistically significant. Okay? At this point, you can make a decision regarding the null hypothesis and the relationship between your variables. The last thing that we do is we present and interpret our results in percents. Okay, and what is a significant chi-square test? Well, chi-square test the relation between two categorical variables. All right, and the null hypothesis means that there isn't a relationship, and the alternative hypothesis means that there is a relationship. Okay, so if the alternative hypothesis is true, chance that an individual falls into a particular category for one variable depends on the particular category they fall into for the other variable. All right, remember degrees of freedom. Example, the relationship between religion and smoking. Is there any? A chi-square test will determine whether being part of a particular religious group makes an individual more likely to be a smoker. If so, then we can say that there is a significant association between religion and smoking. Here's the example. Okay, relationship between good looks and success. Here's success. I'm successful, yes. I'm successful, no. I'm good looking, yes. I'm good looking, no. Okay, so you could see that if I'm good looking, I have successful, yes. Successful, no. If I'm not good looking, I'm successful, yes. I'm sorry, I'm reading it to you backward. If I have success, yes and no. If I'm good looking, no, I wasn't reading it to you backward. So if I have no, if I'm not good looking, I have less success. So our step one is to state the null and alternative hypotheses. The null hypothesis is that there is no relationship between looks and success, and H1 is there is a relationship between good looks and success. Okay, and here are we compute the sum for each row and column. There they are. 5 and 35 is 40, 30 and 10 is 40, 5 and 30 is 35, 35 and 10 is 45. Here's my total. And step 3 is compute the expected frequencies, row total times the column total divided by the total number of observations. And I'm just going to continue on, and I'm actually going to go back and start it again in the next video. Okay, see you there in video 3.